Because the electrons only moved in one direction from the heated metal plate through the positively charged plate at the other end, they behaved in exactly the same way as Bose's semiconductor crystals. But whereas Bose's crystals were naturally temperamental, you had to find the right spot for them to work, these tubes could be manufactured consistently. They became known as valves, and they soon replaced crystals in radio sets everywhere. These discoveries would lead to an explosion of new technology.
Early 20th century electronics is all about what you can do with valves. So the radio industry is built on valves. Early television is built on valves. Early computers are built with valves. These are the things that you build the electronic world with.
Having discovered how to manipulate electrons flowing through a vacuum, scientists were now keen to understand how they could flow through other materials. But that meant understanding the things that made up materials, atoms. It was in the early years of the 20th century that we finally got a handle on exactly what atoms were made up of and how they behaved. And so what electricity actually was on the atomic scale. At the University of Manchester, Ernest Rutherford's team was studying the inner structure of the atom and producing a picture to describe what an atom looked like. This revelation would finally help explain some of the more puzzling features of electricity. By 1913, the picture of the atom was one in which you had a positively charged nucleus in the middle, surrounded by negatively charged orbiting electrons in patterns called shells. Each of these shells corresponded to an electron with a particular energy. Now, given an energy boost, an electron could jump from an inner shell to an outer one. And the energy had to be just right. If it wasn't enough, the electron wouldn't make the transition. And this boost was often temporary, because the electron would then drop back down again to its original shell. As it did this, it had to give off its excess energy by spitting out a photon. And the energy of each photon depended on its wavelength, or as we would perceive it, its color. Understanding the structure of atoms could now also explain nature's great electrical light shows. Just like Geisler's tubes, the type of gas the electricity passes through defines its color. Lightning has a blue tinge because of the nitrogen in our atmosphere. Higher in the atmosphere, the gases are different, and so is the color of the photons they produce, creating the spectacular auroras. Understanding atoms, how they fit together in materials, and how their electrons behave was the final key to understanding the fundamental nature of electricity. This is a Wimshurst machine, and it's used to generate electric charge. Electrons are rubbed off these discs and start a flow of electricity through the metal arms of the machine. Now, metals conduct electricity because the electrons are very weakly bound inside their atoms, and so can slosh about and be used to flow as electricity. Insulators, on the other hand, don't conduct electricity because the electrons are very tightly bound inside the atoms and are not free to move about. The flow of electrons, and hence electricity, through materials was now understood. Conductors and insulators could be explained. What was more difficult to understand was the strange properties of semiconductors. Our modern electronic world is built upon semiconductors and would grind to a halt without them. Jagadish Chandra Bose may have stumbled upon their properties back in the 1890s, but no one could have foreseen just how important they were to become. But with the outbreak of the Second World War, things were about to change. Here in Oxford, this newly built physics laboratory was immediately handed over to the war research effort. The researchers here were tasked with improving the British radar system. Radar was a technology that used electromagnetic waves to detect enemy bombers. And as its accuracy improved, it became clear that valves just weren't up to the job. So the team had to turn to old technology. Instead of valves, they used semiconductor crystals. Now, they didn't use the same sort of crystals that Bose had developed. Instead, they used silicon. This device is the silicon crystal receiver, as a tiny tungsten wire coiled down and touching the surface of a little silicon crystal. It's incredible how important a device it was. It was the first time silicon had really been exploited as a semiconductor. But for it to work, it needed to be very pure. And both sides in the war put a lot of resources into purifying it.
In fact, the British had better silicon devices. So they must have had some growth of silicon already at that time, which we were just started with, in Berlin.
The British had better silicon semiconductors because they had help from laboratories in the US, in particular the famous Bell Labs. And it wasn't long before physicists realized that if semiconductors could replace valves in radar, perhaps they could replace valves in other devices too, like amplifiers. The simple vacuum tube with its one-way stream of electrons had been modified to produce a new device. By placing a metal grill in the path of the electrons and applying a tiny voltage to it, a dramatic change in the strength of the beam could be produced. These valves worked as amplifiers, turning a very weak electrical signal into a much stronger one.
An amplifier is something, in one sense, really simple. You just take a small current, you turn it into a larger current. But in other ways, it changes the world, because when you can amplify a signal, you can send it anywhere in the world.
As soon as the war was over, German expert Herbert Maturay and his colleague Heinrich Welcker started to build a semiconductor device that could be used as an electrical amplifier. And here is that first working model that Maturay and Welcker made. If you look inside, you can see the tiny crystal and the wires that make contact with it. If you pass a small current through one of the wires, this allows a much larger current to flow through the other one. So it was acting as a signal amplifier. These tiny devices could replace big, expensive valves in long-distance telephone networks, radios, and other equipment where a faint signal needed boosting. Maturay immediately realized what he'd created, but his bosses were initially not interested. Not, that is, until a paper appeared in a journal announcing a Bell Labs discovery. A research team there had stumbled across the same effect, and now they were announcing their invention to the world. They called it the transistor.
They had it in December 1947, and we had it in beginning 48, but just life, you know. They had it a little bit earlier, the effect. But funny enough, their transistors were just no good.
Although the European device was more reliable than Bell Lab's more experimental model, Neither quite fulfilled their promise. They worked, but were just too delicate. So the search was on for a more robust way to amplify electrical signals. And the breakthrough came by accident. In Bell Labs, silicon crystal expert Russell Ohl noticed that one of his silicon ingots had a really bizarre property. It seemed to be able to generate its own voltage. And when he tried to measure this by hooking it up to an oscilloscope, he noticed that the voltage changed all the time. The amount of voltage it generated seemed to depend on how much light there was in the room. So by casting a shadow over the crystal, he saw the voltage dropped. More light meant the voltage went up. What's more, when he turned a fan on between the lamp and the crystal, the voltage started to oscillate with the same frequency that the blades of the fan were casting shadows over the crystal. One of Ohl's colleagues immediately realized that the ingot had a crack in it that formed a natural junction. And this tiny natural junction in an otherwise solid block was acting just like the much more delicate junction between the end of a wire and a crystal that Bose had discovered. Except here it was sensitive to light. The ingot had cracked because either side contained slightly different amounts of impurities. One side had slightly more of the element phosphorus, while the other had slightly more of a different impurity, boron. And electrons seemed to be able to move across from the phosphorus side to the boron side, but not vice versa. Photons of light shining down onto the crystal were knocking electrons out of the atoms, but it was the impurity atoms that were driving this flow. Phosphorus has an electron that is going spare, and boron is keen to accept another. So electrons tended to flow from the phosphorus side to the boron side, and crucially only flowed one way across the junction. The head of the semiconductor team, William Shockley, saw the potential of this one-way junction within a crystal. But how would it be possible to create a crystal with two junctions in it that could be used as an amplifier? Another researcher at Bell Labs called Gordon Teal had been working on a technique that would allow just that. He'd discovered a special way to grow single crystals of the semiconductor germanium. In this research institute, they grow semiconductor crystals in the same way that Teal did back in Bell Labs. Only here, they grow them much, much bigger. At the bottom of this vat is a container with glowing hot molten germanium, just as pure as you can get it. Inside it are a few atoms of whatever impurity is required to alter its conductive properties. Now, the rotating arm above has a seed crystal at the bottom that has been dipped into the liquid and will be slowly raised up again. As the germanium cools and hardens, it forms a long crystal like an icicle below the seed. The whole length is one single beautiful germanium crystal. Teal worked out that as the crystal is growing, other impurities can be added to the vat and mixed in. This gives us a single crystal with thin layers of different impurities, creating junctions within the crystal.